Hi everyone, welcome to the second lecture of this module 10 where we are talking about displacement sensors and accelerometers. We are discussing the course on microsensors and nanosensors, and in the previous class, if you remember, we have seen a few kinds of displacement sensor and we discussed that we will continue our discussion on displacement sensor in next few classes. So, in that sense, we are going to discuss today different kind of displacement sensor, and based on this transduction principle, we have not discussed any device yet. So, this new device or new kind of sensor is known as Hall effect displacement sensor, and as the name suggests, this device is based on Hall effect. So, all of us are aware of Hall effect, what is Hall effect, what is Hall voltage and what is Hall resistance. Okay. So, what we will do is we will use those principles to develop a displacement sensor. Okay. So, basically Hall effect displacement sensors are effectively most commonly used magnetic sensor, magnetic displacement sensor. Okay. They are very popular for non-contact measurement of displacement. Okay. So, what happens that when a current flows through a thin conductive strip, mostly semiconductor, but it is also possible with metals. Okay. So, when a current flows through a thin conductive strip and a magnetic field is applied perpendicular to the strip, something like this, very similar to what we have seen in the Hall effect. Okay. You have a conducting strip and there is a way by which current is flowing into this strip, all right, into this strip by applying some voltage. Okay. And a magnetic field is applied perpendicular to the strip. So, say in the upward direction there is a magnetic field applied. A voltage is generated across the strip. So, you will find deflection in voltmeter across this strip. Okay. So, basically this voltage is the Hall voltage, and we use this voltage for the measurement of displacement. Okay. So, the magnitude of this voltage is directly related to the strength of the magnetic field. Okay. So, and the strength of the magnetic field varies with the displacement if the conductor that is in the vicinity is moving. Okay. So, displacement of the magnetic source, mostly in the form of magnet or some ferromagnetic material, okay, changes the magnetic field, magnetic flux density at the sensor. Okay. The sensor outputs a corresponding voltage signal which is proportional to the displacement. So, this is the basic principle behind this Hall effect displacement sensor. So, a magnetic source which can be a magnet or a ferromagnetic target is moving in the vicinity, and because of that the magnetic flux density at the sensor is changing. Okay. And accordingly the sensor output, which is basically a electrical output, it can be mostly voltage, is changing, and this voltage change is proportional to the displacement. Okay. This Hall effect displacement sensor, they can be linear or they can also be rotational. Okay. But usually they come in two main types, both of them. One is the analog one, and another is bi-level devices, which is having a predefined thresholds. Okay. So, this is a basic layout of a analog type Hall effect displacement sensor, and this is a bi-level or you can say the similar sensor working in a threshold mode. Okay. So, you have a circuit for providing threshold. We will see it can be a Schmidt trigger also. Okay. So, this is a circuit to provide threshold. All right. We will see how this is helpful in designing this Hall effect displacement sensor. Okay. So, first one, the analog sensors. The analog sensors typically include a amplifier, okay, to simplify the interfacing with the peripheral circuit. So, this is your amplifier, which is the output of this is fed to a interface circuit. Okay. So if you see, you have a regulator and a Hall sensor whose output can be say in plus or minus depending on the movement of the object. Okay. And also depending on what type of semiconductor I am using for the bar, this will vary. Okay. However, the response to magnetic field is not perfectly linear, and a typical curve for the output voltage versus magnetic, this is the x-axis is magnetic flux density, okay, and the unit is Gauss. Okay. Their response, if you see, is not linear. Okay. Although it is, the non-linearity is not very high, but then also this device is not considered as linear device. Okay. And you require frequent calibration for accurate measurements. Okay. However, a bi-level sensor or the sensor operating in threshold mode, in addition to this amplifier, there is a Schmidt trigger with a built-in hysteresis at the threshold level. Okay. Now, the output signal as a function of the magnetic field density is shown in this figure. You have already seen this for a analog Hall effect displacement sensor. Okay. If you see this curve, what you are finding is you have a hysteresis, and this hysteresis is provided by this Schmidt trigger. Okay. The signal is, as the name suggests, it is a bi-level Hall effect displacement sensor. The signal is of 2 level and has a clearly pronounced hysteresis with respect to magnetic field. Okay. When the applied magnetic flux density surpasses a predefined threshold, the trigger produces a sharp transition from off to on. Okay. There is a sharp transition from off value to on value, and this introduction of this hysteresis in this device is very helpful. This hysteresis prevents unwanted oscillation by creating a deadband zone during which no action occurs after the threshold is crossed. Okay. So, if you remember, we have already discussed the deadband zone in case of our discussions on different primary or say static characteristic of a sensor, and in that we have seen that if this is my say input stimulus, say this is a curve of this or a transfer function of a sensor in the form of say output voltage, say I am calling it V out versus the input stimulus. Okay. I am calling it say stimulus. Okay. All right. We have seen that. So, deadband was somewhere near to 0 where the device was not operational, although we were trying to the input was kept on increasing, but there was no change in the output, right. However, after this deadband is crossed, the sensor responded clearly. Okay. So, that is what this Schmidt trigger do. Okay. It exactly have the same principle. It introduces a hysteresis which acts as a deadband, and this deadband will help sometime to avoid any unwanted oscillation or false positive during there is no action or there is certain kind of vibration or something. Okay. So, this hysteresis prevents unwanted oscillation by creating a deadband zone during which no action occurs after the threshold is crossed. Okay. Now, Hall sensors are mostly manufactured as monolithic silicon chips and enclosed in a compact epoxy or ceramic packages, and its packaging is very crucial, particularly for magnetic shielding and other purposes. Okay. The advantage of this kind of sensor, if you see, is you are able to monitor the displacement in non-contact mode. Okay. And these devices, as I have mentioned, that the fabrication involve a single monolithic silicon chip, they are very durable. Okay. and since there is also no moving part in it, it is not as fragile as other sensors are. Okay. Their accuracy level is very high because magnetic field is involved. Okay. And the repeatability is also very decent. Okay. The devices can be made as small as a 1 or 2 mm or even smaller. Okay. So they are very compact. Okay. These devices are not that power hungry, so you can say that they are categorized under low power devices. Okay. And they have a very wide operating temperature range, which is very essential for operation of this kind of devices in harsh conditions. Okay. So these devices can be used in those kind of conditions. Okay. However, please note that when I say harsh conditions, it means that the variation in temperature, humidity, those things are allowed, but not the variation of external magnetic field. So that is the limitation of this device, that it cannot operate in conditions where large magnetic field is available externally. Okay. So in that cases, that can affect the magnetic flux density because of the movement of the object which is under investigation, and therefore it can cause interferences. Therefore, this is one of the limitation of this Hall effect displacement sensor. Okay. Then this device has a limited range, and that will depend on the magnetic strength of the object which is in the vicinity and whose displacement we are trying to detect. Okay. And they require a precise alignment for linearity. Okay. So although you can still harvest the linearity part from this non-linearity data, but the alignment is very important, because you have a cross product involved in this equations of this Hall effect, and because of that the angle between electric field and or the current flow and magnetic field will affect the linearity of the device. Okay. So because of these things, these devices, although is very popular, but for specific applications you may have to look for other kind of devices. Okay. So next kind of device that we are going to discuss is a magnetoresistive displacement sensor, and again it is also based on magnetic principles. Okay. Basically based on magnetoresistive effect. We'll see what is a magnetoresistive effect in very brief, and we'll see how this sensor functions. Okay. So magnetoresistive displacement sensor can be manufactured for detection of both linear as well as angular displacement, and mostly it measure based on this magnetoresistive principle, which is the change of a resistance of a material due to external magnetic field. Okay. And this is not present in all kind of material, so you have to have specific kind of material which shows magnetoresistive behavior. Okay. When I say magnetoresistance, magnetoresistance refers to the property of a material, whether it can be a metal or it can be some semiconductors, it can be some perovskite kind of material, depending on what kind of magnetoresistance you are talking about. Okay. So this magnetoresistance refers to the property of a material where its electrical resistance alters in response to an applied magnetic field. Okay. So when you apply a magnetic field, the resistance of the semiconductor or a metal changes. Okay. So this change of electrical resistance in presence of magnetic field is characterized under magnetoresistance. Okay. So this phenomena is very important for several applications, including the displacement sensor fabrication. Okay. So a magnetoresistor is used to detect the presence, strength and direction of a magnetic field. Okay. And it is typically made from semiconductor materials, for example indium antimonide or indium arsenide, but then there are other examples also, including some metal, particularly the heterostructures of metals. Okay. They show various kind of magnetoresistance. Okay. So the resistance of a magnetoresistor increases proportionally with the strength of the magnetic field, okay, and this change in resistance is a result of magnetoresistive effect. So one of the characteristic curve for magnetic resistor is shown over here, where you have this y-axis as a change in normalized change in resistance, and this is for normalized magnetic field, okay. So the sensitivity of a magnetoresistor is influenced by the strength of the applied magnetic field, okay. Now if you see the basic principle behind the displacement sensor based on this magnetoresistive property, the sensor as the name suggests contains a magnetoresistive element. It can be, as I have mentioned, it can be a metal or it can be a semiconductor, and when this magnetoresistive element is exposed to a magnetic field, its resistance changes based on the direction and strength of the magnetic field, okay. Now as a magnet or say magnetic scale moves relative to the sensor, the magnetic flux through the sensor actually changes, right, because of its movement, and this change will cause a measurable change in the resistance, okay, and this change is converted into electrical signal which is proportional to the displacement, and that is how this kind of devices work. Okay. There can be a number of magnetoresistance depending on what principle it is using. For example, you can have giant magnetoresistance, which is known as GMR. Okay. You can also have AMR, which is anisotropic magnetoresistance. Okay. Then you have a tunnel magnetoresistance, which is TMR, and then you have colossal magnetoresistance, which is known as CMR. Okay, and then you have extraordinary magnetoresistance, which is known as EMR. Okay, so you have a number of magnetoresistance, and nearly all of this principle can be used for developing a magnetoresistive displacement sensor. Okay, so if I talk about anisotropic magnetoresistance or AMR, AMR is a phenomena where the electrical resistance of a ferromagnetic material changes depending on the angle between the direction of electric current and magnetization of the material. Okay, if this is the say magnetic material and the magnetization is in this direction and the current is in this direction, and if the current direction is changes because of some principle of or if this object is having some rotational movement. Okay, so if you have this current flowing, okay, and this is the object, okay, and the magnetization was in this direction, and by some mean if this magnetization changes its angle with respect to the direction of current, you will have change in the resistance of the material, okay, or the element, magnetoresistance element, okay, and this kind of principle or this kind of phenomena is known as AMR. So you can clearly use this kind of devices for displacement measurement. Okay, then you have giant magnetoresistance. Basically this is a quantum phenomena, and in this phenomena the resistance of the magnetoresistor decreases when magnetization is aligned in a parallel direction. So you have say consider this first case where the magnetization is aligned in a parallel direction. Because of this the resistance decreases, and that is why it is showing some LED is glowing, because it is forming some conductive path. Okay. Now the resistance significantly increases when magnetization is aligned anti-parallel. So when you have magnetization like this, please note that this is some kind of spacer, okay, which is between two different metals. Okay, and when you have this kind of magnetization in anti-parallel direction, okay, the resistance becomes very high between these two, in this path, and because of which it is showing that the it is showing that this is not a conductive path. Okay, and it's a very high resistive path, and it shows that the resistance increases when magnetization is aligned anti-parallel. Okay, by which I mean if the resistance is increasing or decreasing means it is showing the magnetoresistance property, and since this resistance change is very high, it is known as giant magnetoresistance or GMR. Okay, then you have extraordinary magnetoresistance. In this effect, the resistance of the metal or semiconductor is high, mostly the metal semiconductor hybrid kind of material, okay, is high when there is no magnetic field and low when a magnetic field is present, okay, and this changes is also very high, okay. Then you have tunnel magnetoresistance. Again, since tunneling is involved, means that it is also a quantum effect, okay. The current flows from one ferromagnetic electrode through the insulating barrier. So this is the insulating barrier, and these two are, for example, ferromagnetic electrodes, okay. The magnitude of the tunneling current depends on the relative direction of the magnetization in the electrodes, okay. Now you have another kind of magnetoresistance which is known as CMR, okay. So colossal magnetoresistance, CMR, is a phenomena where certain material exhibit a dramatic decrease in electrical resistance when exposed to magnetic field, and please note that it is very similar to GMR. However, this is not a quantum mechanical phenomena, and mostly this is classical mechanic phenomena, and mostly shown by some perovskite, particularly based on, say, manganese, okay. Then, as I have already mentioned, that these magnetoresistive displacement sensors operate very similar to Hall effect sensors, and they require some external magnetic field to function, okay. However, if you remember, Hall effect sensors were totally different. There were not much resistance drop because of magnetic field and other things, okay. However, people has tried to connect Hall effect phenomena with this magnetoresistive displacement sensors, but what we are trying to discuss in this sensors course right now is they are two different phenomena, okay. So when magnetoresistive sensors are used for detecting proximity, position or rotation, they must be paired with a magnetic source, okay. The advantage of this kind of devices are they are highly sensitive and they have very good resolution, particularly in the case of GMR, okay. They have a wide measurement range, okay. These devices are not very heavy because some of the devices can be built by using thin film of a few nanometer thick metals, okay. So they are very compact and they are very lightweight, okay, and they also operate in non-contact operation mode, okay. And since this electrical changes is because of external magnetic field, they are having good performance and having less dependence on temperature, okay. However, as they are using magnetic field for the measurement, they are very sensitive to external magnetic interferences, okay. They may also require a certain kind of temperature compensation, okay, and calibration is needed for precise applications of for certain important application of this magnetoresistive displacement sensors. So they also have these limitations, okay. So in brief, I think we have talked about a number of displacement sensors, including some capacitive based devices, some magnetoresistive devices, some Hall effect based devices. I think we have covered entire spectrum of displacement sensors. We have not discussed till now optical displacement sensor. I think that we can cover in our next lecture. Along with that, what we are going to talk in our next lecture is accelerometers, okay. Accelerometers are very important devices, particularly for electronic gadgets like your mobile phones, for example, okay. All these devices are equipped with accelerometers, okay, and they are being used by number of applications, including several video games, okay, including various mobile games, okay. So accelerometers are very important. What we are going to do in the discussion of accelerometers is we will figure out till now what we have seen is we have talked about various static and dynamic characteristic of these sensors, and we have talked about them in context of each and every sensor, be it a chemical sensor, be it a physical sensor including some humidity sensor or some say displacement sensor and all those things. Everywhere we talked about very similar static characteristics or dynamic characteristics that we have talked in the first module or second module, okay, including some say linearity, response time, recovery time, hysteresis, then selectivity, then you have reproducibility, repeatability. All these things we have seen in our initial modules, and we have used it over this 10th module, okay. However, since as I have mentioned that accelerometers are very important for device point of view or a gadget point of view, companies or industry is very much interested in all these accelerometers, okay, and therefore the performance analysis of these accelerometers cannot be restricted to the static and dynamic characteristic that we have seen for most of the sensors. So what we will do in our next lecture is we will bring some of the new characteristic which is only relevant to a accelerometer. Okay. Of course, we will see different type of accelerometer, and we will also see different fabrication strategies to develop this accelerometers. But what we are going to do is we will first talk about various important characteristic which is exclusively applicable for this kind of accelerometers. Okay. And then we will see some unconventional kind of accelerometers which is very specific to a particular company, which is copyrighted by certain agencies. Okay, we will try to understand it from various perspective, and we will also talk like what we can further do for the fabrication point of view as well as from the application point of view. So